For joining us for this episode 2 of the 3-part CMEO cast series. This one's entitled From Bench to Bedside, Applying Clinical Updates to Treatment Planning for Patients with Narcolepsy. The episode that we're going to be discussing tonight is Navigating the Neurophysiology of Sleep and Cataplexy, the Significance of Select Neurotransmitters. This podcast series is supported by an educational grant from Harmony Biosciences. I'm Michael Thorpe, Professor of Neurology at the Albert Einstein College of Medicine and Director of the Sleep-Wake Disorder Center in the Department of Neurology at the Montefiore Medical Center in the Bronx, New York. I'm joined today by my friend and esteemed colleague, Phyllis See, Professor of Neurology and Chief of the Division of Sleep Medicine in the Department of Neurology, as well as Director of the Center for Circadian and Sleep Medicine at Northwestern University Feinberg School of Medicine in Chicago, Illinois. To start off for our discussion today, what I'd like to do is to review our learning objective. Our goal is that after the CMEO cast episode, you'll be able to differentiate the various neurotransmitters that are involved in cataplexy and the sleep-wake cycle, including their impact on wakefulness. So let's start. So Phyllis, why don't you tell us a little bit for a start about how normal sleep is controlled and disturbed sleep is affected?
Excellent. Well, it's Dr. Thorpe, sleep and wake cycles are regulated by brain activity, and the EEG and the motor activity that we measure in our sleep studies are really excellent biomarkers for measuring sleep and wake states. There are, as you can see, there are two primary sleep stages, what we will call non-REM sleep and also REM sleep. Non-REM sleep accounts for the majority of sleep during the night. They are actually very distinct physiological states. Normal sleep includes really these dynamic cycles, as you can see here, between REM and non-REM sleep. Mm-hmm. And there's very few awakenings and arousal, so sleep is fairly well consolidated. And during the wake time period, during the day, you can see individuals are able to stay awake throughout the entire day. Whereas in abnormal sleep, for example, in a patient with narcolepsy, you see the fragmentation of sleep during the night. You also see that there are more REM episodes, especially early REM latency during the nocturnal sleep period, as well as frequent napping and also REM sleep intruding into wakefulness.
Now, of course, REM and non-REM sleep and wakefulness don't all just happen by themselves. Something has to be causing those states to occur. Can you tell us a little bit about the nuclei in the brain, particularly those responsible for wakefulness?
Well, the regulation of wake is really, really important because I think being able to stay awake is really an essential part of this biological drive. So as you can see, it's not surprising then that there are multiple areas and multiple levels of the brain where from the brainstem to the thalamus to the hypothalamus and all the way projecting to the cortex that regulate wakefulness. So it's very a redundant system. One of the important systems are the monoaminergic systems, which produce, of course, the monoamines. And there is important for driving both arousal and maintaining wakefulness. So you
now,
see
the main monoamines consist of what, Phyllis?
Well, the monoamines consist of norepinephrine, which is generated in neurons from the locus coeruleus. Also, serotonin, which is from the dorsal raphe nucleus, dopamine, which is from the ventral tegmental areas you can see, and also histamine, which is from the tubulomammillary nucleus. And all of these are excitatory and they promote wakefulness.
Now, a lot of people don't realize that acetylcholine is also involved in alertness and wakefulness, isn't it?
Absolutely. And you can see in the slide that acetylcholine, one of the major sources is in the area called the basal forebrain, and that can project cholinergic pathways to the cortex itself. But in addition to that, there are cholinergic nuclei in the brainstem, such as peduncle pontine tegmental area and the lateral dorsal tegmental area, which you can are also called areas of cholinergic innervation and activation, and they activate more the subcortical areas of the brain, as well as, but also projections and also affecting the orexin system.
So one of the neurotransmitters that's involved in wakefulness that most people have heard of is dopamine. So what does dopamine do in the brain, and where does that come from?
So dopamine originates primarily from the ventral tegmental area and also the substantia nigra. And as you can see, it really projects to other areas of the cortex. And it really is wake promoting and activation of cortex and also other areas in both the thalamus and hypothalamus.
And how about norepinephrine? That's also involved in wakefulness, as you mentioned earlier. So where does that largely come from?
Yeah, very important. I think norepinephrine originates from neurons in the locus coeruleus, which is in the brainstem area, as you can see. And again, this small nuclei projects to the cortex, to the thalamus, and regions that really promote and activate the brain.
Now, many years ago, I know people used to think that serotonin was involved in producing sleep, but now, of course, we know that it's important in alertness. So where does serotonin largely derive from in the brain?
Indeed, serotonin is really more thought to be a wake-promoting neurotransmitter, and it originates from neurons in the dorsal raphe nucleus. Again, very similar to the other monoamines, it does also project to the thalamus, but also to the cortical areas to activate the brain.
Okay. And then there's histamine. You mentioned histamine earlier. I think that's a sort of a relatively newly recognized neurotransmitter that's involved in wakefulness. Could you tell us a little bit about histamine?
Yes, absolutely. We all know that antihistamines, right, make you sleepy to some extent. And therefore, histamine, it originates from neurons in a small nuclei called the tuberomammillary nucleus. And when it's activated, it's a monoamine that activates, it's excitatory to the brain regions. And what's really interesting to me is that it also projects to other areas, like the locus coeruleus and other areas that are also wake promoting.
Okay. And finally, one of the main neurotransmitters that we've really learned about in the last couple of decades is this neuropeptide called a Rexin. What does a Rexin do in the brain?
Orexin is very important, and you're absolutely right. Only in 1999 where we really become really aware of its role. It's located in the lateral hypothalamus, a group of neurons, and there's two. There's orexin A, orexin B, and as you can see, it projects to, again, cortically to activate the wake promoting regions, but also projects to all these monoaminergic areas, the tuberomammillary nucleus, also to cholinergic areas of the brain. So it's really in many ways a stabilizer of wakefulness. And there's some studies to show that if you want that it's one of its primary roles is to be able to allow an individual to stay awake for prolonged periods of time.
Now, when we started off, you talked about how sleep was affected, particularly in narcolepsy. You gave that example where it was disrupted. We know that REM sleep is very important in narcolepsy, and that it is involved not only in the dreams and the cataplexy and the muscle paralysis of narcolepsy. Can you just tell us a little bit about the REM neuron system? How does that actually work? What cell groups are involved in producing REM sleep?
Yes, absolutely. So typically, I think even in, until very recently, we really thought that the cholinergic system is really the most important and perhaps the regulator of REM sleep. Indeed, it is very important because activation of the cholinergic system, especially in the areas of the pons or in the brainstem, such as lateral tegmental area, the ventrolateral preoptic area, all of these things are going to be important. So indeed, REM sleep is thought to be largely regulated by the cholinergic system. So activation of acetylcholine is going to be important in not just maintaining wakefulness, but also REM sleep. So glutamate also plays an important role, and particularly the area of the subcereus, or we can also call it, sometimes it's called the sublateral dorsal nuclei. And it's called that because, as you can see, it's just kind of dorsal or a little caudal to the locus coeruleus area. So when the SLD is activated, it excites also the inhibitory glycine neurons in the spinal cord. And this is how in REM sleep, we also get what we call atonia, or your muscle activity, especially in the spinal area, is decreased. And as we know, in patients with narcolepsy, there are abnormalities in that region, partially because the orexin system is also impaired.
So in the normal situation, the orexin system is active while we're awake. And of course, we're not going to have REM sleep or the muscle paralysis of REM sleep while we're awake. So what happens in narcolepsy when you cut off the orexin stimuli to those nuclei that are important in REM sleep, and how does that affect our muscle activity in narcolepsy?
Well, as we heard, orexin is really an important neurotransmitter for maintaining wakefulness. So if you cut, and also for maintaining motor activity, motor tone when you're awake. So when you cut off orexin, or there's impairment of the orexin system, you will then, it will result in reduced activity of this ventrolateral periaqueductal gray area and the lateral pontine tegmental area, and also the dorsal raphe and locus coeruleus. These are all wake promoting regions, right? But in particular, when you, and now also there's going to be involvement of the sublateral dorsal nuclei, or the subcoeruleus nucleus. And then what you get, rather than normally during wake, you have the activation, but now when during sleep, in REM sleep, when you have a lack of orexin, now you get activation of the motor neurons, which is really the abnormal state.
So it stops the inhibition of the sublateral dorsal nucleus so that it then can cause the muscle atonia of cataplexy.
That's right. But then during wake, in somebody with, let's say, narcolepsy, what's happening is now you're allowing this motor atonia, right, to be to intrude into wakefulness. And one say, well, why would laughter or these strong emotions trigger something like cataplexy? And you can see is because the orexin system, in particular, also has inputs to the amygdala, and so are the wake promoting centers. And when you have that inhibition of the orexin system, it could potentially further trigger, the emotional content can further trigger this motor atonia or cataplexy during wakefulness.
So let's talk now a little bit more in detail about the neurotransmitters, and particularly how they're affected at the synaptic level. Can you talk a bit about dopamine, norepinephrine, and serotonin? What happens there at the synapse?
Absolutely. So when you have high dopamine tone, as you can see at the synaptic level, it will promote wakefulness, whereas low dopamine tone will enhance the propensity for sleep. As we said earlier, norepinephrine is really kind of a key arousal, and at the synaptic level, how do you get higher norepinephrine levels? You can actually release more norepinephrine, or you can change it by changing the reuptake of norepinephrine at the synapse. So as we'll see a little bit later, there are different medications that can either release more norepinephrine and or decrease its reuptake.
So most of these neurotransmitters have reuptake mechanisms that potentially could be blocked to cause a greater amount of the monoamine in the synaptic cleft. Is that right?
Correct. And many of our wake promoting agents on the market are indeed use that mechanism of being inhibiting the reuptake of these monoamines.
So let's talk a little bit about histamine, because that has a slightly different sort of mechanism, because there's a different sort of receptor involved here, isn't there?
Yes, histamine is very interesting. I think, you know, we already know that it is, when it's activated, it will promote wakefulness, but it has different types of receptors. It's got the, you know, you got H1, H2, they're postsynaptic receptors, as well as there are presynaptic receptors. And the H3 is really very, very interesting because it is a presynaptic. So what it does when it's activated, it actually, it's kind of like an auto inhibition. And by doing that, it actually promotes further release of histamine.
Okay, so we've talked a lot about the neurotransmitters involved in producing wakefulness. We haven't talked so much about what causes actual sleep, but can you, in a sort of an overview type of way, can you talk a little bit about the regulation of sleep and wake and how these neuronal groups interact to cause the cycling of sleep and wakefulness?
Yes, absolutely. So, you know, sleep, especially non-REM sleep, is in many ways a kind of an active inhibition almost of wakefulness. So there are two areas in the hypothalamus, one called the ventral preoptic nucleus and the other called the median preoptic nucleus, where they their neurotransmitter is GABA, and in the VLPO, it can also be galanine. And as you can see, that GABA, when it's activated, will inhibit the orexin system, and also most of the all the monoaminergic and cholinergic systems that are promoting wakefulness. But then when the system is activated, when the monoamines, the wake promoting nuclei are activated, they promote wakefulness. So it's really in many ways a balance and kind of interaction, activation, mutual inhibition of this wake and sleep promoting system. But central to this, again, is the orexin system, where you see right there, which promotes the stability, right, of both wake and sleep states.
Okay, so let's now talk a little bit about the medications that were used to affect the sleep-wake cycle, in particular, improving alertness. Can you give us a sort of a conceptual model of the pharmacological approach towards affecting these neuronal groups for influencing our alertness?
Yes, of course. So when we talked a little bit earlier about different levels of the brain where we regulate sleep and wake. We looked at the cortical level, the cortex, the hypothalamic area, like where the orexin system is, where the sleep systems are, and also at the brainstem level where REM sleep is generated and very, very important for. So if we look at something classical like GABA, that will promote sleep when it's activated, and it affects the system, the neural system at multiple levels. If you look at histamine, it is from the hypothalamus. It can also affect the thalamus, and also, again, at multiple levels, both at the cortical level, but also at the brainstem level, to promote wakefulness and arousal. The orexin system, as we had mentioned earlier, promotes wakefulness because it does project to almost all the wake promoting regions of the brain, but also in that way stabilizes the wake state at multiple levels of the nervous system.
So we now have quite a variety of different treatments that are available for narcolepsy, and of course they affect these neurotransmitters that you've been talking about, and so have a beneficial effect upon excessive daytime sleepiness and cataplexy. Modafinil, for example, is one that affects the dopamine system, so that it affects a dopamine reuptake inhibitor, and so it increases dopamine, and so it has a very positive effect on excessive daytime sleepiness. Modafinil, a longer-acting form of modafinil, also works through that dopaminergic mechanism to improve alertness and wakefulness. Then we have this new medication called solriamfetol, and this both works through dopamine and norepinephrine. So it is a reuptake inhibitor, so it increases the synaptic levels of both dopamine and norepinephrine, and so has a positive effect on excessive daytime sleepiness. Then there's pitolisant. Pitolisant is a drug that affects the histaminergic system. And so it works in a different way. It's a H3 receptor antagonist or inverse agonist. So the result is that it blocks the H3, the histamine 3 receptor, and leads to an increase in histamine in the brain that produces wakefulness. And this has been shown to be effective not only for excessive daytime sleepiness, but also cataplexy. Then we have Oxibate. And there are different forms of Oxibate, one sodium formulation and one without sodium. These work through a different mechanism. These work through a GABA B receptor mechanism and tend to influence those monoamines that you were talking about, Phyllis. And Oxibate is very effective for both excessive daytime sleepiness and cataplexy. And not only in adults, all the previous drugs I mentioned FDA approved for adults, but Oxibate is FDA approved for children as well. And then finally, we have the traditional stimulants like the amphetamines and methylphenidate. They affect a wide range of monoamines. So they affect not only dopamine, norepinephrine, but serotonin as well. And they can have beneficial effects in narcolepsy, particularly on excessive daytime sleepiness. And they are available for adults and children, but they tend to have more wide-ranging effects and are becoming supplanted by some of the newer agents that I just mentioned. Okay, so Phyllis, thank you very much for highlighting all these key neurotransmitters that are involved in sleep-wake regulation. And so that now that we know about the transmitters and we can understand a bit better how these medications are going to affect sleep and wakefulness by influencing those monoamines and other systems. And for example, a Rexin. In the future, we're going to have drugs that will affect the Rexin system. So in conclusion, then sleep, it's a crucial biological process. It's regulated through complex interactions between multiple brain regions, as you talked about, Phyllis, and also many different neurotransmitters. So several of these neurotransmitters are involved not only in alertness and wakefulness, but also in sleep. So the monoamines, GABA, histamine, or Rexin are all important areas of attention for affecting sleep and wakefulness. So it's important for people to understand how targeting therapies on the various receptor types can affect the sleep-wake cycle, but in particular, they can affect excessive daytime sleepiness and cataplexy, and so be most important in the treatment of patients with narcolepsy. So let's summarize our SMART goals. SMART stands for specific, measurable, attainable, relevant, and timely goals. And these are the main points that we would like our audience to take away today. One is identify key neurotransmitters involved in the sleep-wake cycle. So understand how targeted therapies can affect these neurotransmitters so that they can affect the sleep-wake cycle. And as mentioned, a number of these medications will work on one or other neurotransmitter and will have differential effects, either affecting more the REM process or the general alertness, or inhibiting the sleep-wake process. So it's important to recognize that these neurotransmitters are all important targets for the sleep-wake cycle. Well, Phyllis, I'd like to thank you very much for joining me today to discuss the neurotransmitters and the neuronal systems involved in the control of sleep and wakefulness, and particularly how they're affected in narcolepsy. So I'd like to thank you and also our audience for joining us. Be safe, take care of yourselves so that you can provide the best care for your patients.
Thank you.